about statements in this class, not just English statements. We talked about mathematical statements. Mathematical statements like P, Q, sometimes we denote them by A, B. We learned that if we have a mathematical statement, we can assign only two values to those statements. It cannot be both true and false. So the statements, mathematical statements, they don't depend on something. You can verify that if they are true or false. Very well. So we have some statements that apply to all variables or all objects. For example, suppose I write this as x plus 1 equal to 0 has a solution. This is a statement. You can easily solve this equation, and the equation has a solution which is -1. You already know that. This is just a super easy pre-algebra equation. So in general, we write it this way. We say that for all, for any, if I find some value that satisfies this equation, that value is the answer. Well, is it actually for all, or is it just for exactly one value? What's the difference between this statement and this statement? X squared greater than equal to 0. So I want you to think about this. I have two statements, and for one of them, I'm allowed to use for all, for any random value, for all. For one of them, I can only use there is, there exists. So which one can be connected to these two statements? Is this guy true for all values of x, or is this true for only one value of x? This is only true for one value of x, which is -1. So there is one solution for this statement. It's not true for all x values. For example, if I plug in 0 for x, 1 is equal to 0, which is not correct. But this guy is true for any random value for x. So this statement is connected to for all. Very well. So instead of writing these in English format, we are trying to come up with some symbols that help us to write this in nice and compact form. So let me erase these. There is a solution for x plus 1 equal to 0. For all x values, x squared is greater than equal to 0. Well, we can translate these two statements into mathematical form, logical form, this way. So the transition is going to be there is, there exists. We're going to use quantifier that we call existential quantifier. It is flipped capital E. So we say that there is existential quantifier. This is existential quantifier, and we read it as there is. there is one x value such that x plus 1 is equal to 0. The transition from statement into logical form for the second example is going to be for all. For any random value of x, if I square that, it's going to be greater than or equal to 0 for any of them. Take radical, take fractions, take anything that you like. So the quantifier that you're going to use is upside down A, and we call it universal quantifier. Universal quantifier. And you read it as for all, for any, for every, for all values of x. If I square it, it is going to be greater than or equal to 0. These statements are called quantified statements. So let us write a note. A quantified statement is either a universal statement which is written as for all x belongs to a domain. So officially, we're going to add a domain as well, such that a statement is related to x. Existential statement which is written as there exists an x value in the domain such that, and a statement related to. So these are called quantified statements. Very well. So we usually call px and qx the predicate. Let's write down the official definition of predicates. So a predicate, definition of a predicate. A predicate is a sentence, or it can be a formula, anything that includes one or more variables. So each one of these are called a predicate. P of x and q of x. We denote them by P of x. You might have more variables. P of x and y, and so on. Depending on your statement, depending on your sentence, you add more variables. Well, note that we have something that we call truth set. Truth sets are the actual values that the predicate is actually true for those values. So truth set is equal to the set of all values in the domain, all x values in the domain, such that the predicate is true. is true. So note that we talk about domain, we talk about the predicate, and we talk about truth set. Well, give us an example. Example. So let us first specify the domain. Let D be n natural numbers and we say that our predicate is Q of n, which is defined as n is a factor of 8. N is a factor of 8. And n belongs to D. And the domain is natural numbers. The question says, what is the truth set of Qn? Very well. So the domain is just n, the natural numbers, and we're looking for the factors of 8. Factors of 8. Factors of 8. Or divisors of 8 are equal to the set of 1, 2, 4, and 8. So the notation that you're going to use is 1 divides 8, 2 divides 8, 4 divides 8, and of course 8 divides 8. So the vertical line here is divides. It divides 8. So let's continue. So here's a question. What if the domain is equal to positive integers? Question. What if the domain is Z? So what are the truth sets for this predicate if I change the domain into positive integers and also integers? Very well. So if we change the domain to positive integer, it's going to be the same as natural number set, and the truth set is going to be the same. But if I change the domain to Z, remember Z includes positive and negative numbers. So the truth set includes plus minus 1, plus minus 2, plus minus 4, and plus minus 8. Remember that both positive and negative numbers can be divisors or factors. Negative 1 divides 8, negative 2 divides 8, negative 4 divides 8, also negative 8 divides 8. So if we change the domain, we have to be careful about the truth set.